Okay, so in yesterday's class, we looked at lattice energy and we came up with the definition that we're going to use to describe lattice energy. So first thing I want you to do as kind of a starter is pause the video and just say out loud to yourselves what the definition or our definition for lattice energy is. Okay, so hopefully you've defined it as the energy that will form 1 mole of an ionic compound, okay? And that is from scattered gaseous atoms. You might not have had it in exactly those words, but that will make sense. Okay, probably the best way to define it is by doing examples. Okay, and yesterday at the end of the class, I think I gave you 3 examples. Where are they? Okay, so these were taken from the textbook. I wanted you to display the equation that illustrated lattice energy for magnesium oxide formation, potassium bromide, and sodium sulfide. So let's do those 3 now, nice and easy. I've already forgotten what the first one was. Magnesium oxide, okay? So key point here is that magnesium, those ions, must be as scattered gaseous ions. So you've got magnesium there and you've got oxygen there. Again, you should know these charges off by heart, shouldn't be a problem. Magnesium group 2, oxygen group 6. And then you're going to form magnesium oxide. And remember, it's forming of 1 mole of magnesium oxide, which makes perfect sense. And that's a solid there. Okay. The second example was, let's go back, potassium bromide. Okay, nice and easy. So we've got potassium, group 1 metal. Again, make sure you put the state symbol in, it's a gas. Bromine, group 7, 1 minus charge there. Okay, so we should have KBr. Now, I want you to think about the things that are missing here, okay? So I've kind of done that incomplete. I'll give you a few seconds, pause the video, and just put in things that are missing. Right, so I'll just quickly change the color of my pen here. So by definition, it has to be from the scattered gaseous ions. So I missed the gas symbol there, and also I've missed the state symbol here. Okay, everything else was fine. Switch back to the black pen. Okay, our third example, I've obviously forgotten it. Okay, third example was sodium sulfide. Okay, this isn't a compound that you're going to be as familiar with, but it's pretty straightforward. Okay, sodium, again, group 1, sulfur, same group as oxygen, so we're looking at a 2 minus charge there. We've got slightly different, slightly more thinking to do here, but it should be nice and straightforward. You know that's going to form Na2S because of having to balance the charges in the ionic compound, okay, with sodium being 1 plus and sulfur being 2 minus, okay? Again, I've got things missing. Pause the video and make sure that you've put in the missing things. So once again, it was the state symbols that were missing. Remember, by definition, we're talking about formation of a mole of ionic compound from scattered gaseous ions. Okay, so okay, it might seem a bit like childish for me to be stopping the video and asking you to fill those things in, but obviously, in an exam, you'll only get the marks if you have those state symbols in there, okay? So it's very, very important you just get in that habit of making sure you do it. Okay, the other thing I wanted to make very clear is in yesterday's class, I was referring to lattice energy as just delta H the whole time, really, because I was just talking about energy in general. But we do have to make sure that we use the correct expression here, okay? So from now on, when we're talking about lattice energy, we're going to make sure we express it like this, okay? Delta H, this little symbol here, I don't know, is that called theta? Not sure, but that symbol there, and then lat. Okay, it's a bit of a hassle really doing all that, but that's how we need to express the symbol for lattice energy. And the reason why that's really important is because you're going to be learning about other types of enthalpies in a moment, which also have their definitions and their different way of expressing them. So from now on, lattice energy is expressed like this, okay? Please make sure you've written that down. And the other thing to bear in mind is that this value is always going to be negative according to the way you define it. And that's because, just a quick recap then, it's because we're talking about the forming of the ionic compound, aren't we? Okay, and the compound form is always going to be more stable than the ions from which it is formed. Okay, so this could represent, for example, yesterday I think we spoke about Na plus and Cl minus. So they're up there on this level of energy. Okay, let's say we've got to put G in there, haven't we? And then we've got our actual ionic compound here, which is far more stable, far less likely to want to do anything. And therefore the difference in energy here, this difference, if I drag that line across, is going to be a negative difference effectively. So we've got an exothermic process, okay? And a negative value for the lattice energy. Right, okay, now today's lesson is going to be pretty much all about calculating lattice energy. And so if you have already looked at your textbook and kind of gone through their explanations of how to calculate lattice energy, I don't like the way they do it. Similar to when we did the enthalpy changes topic, chapter 6, I felt that them using energy cycles was overcomplicating things, increasing the chance that you'd make a mistake. Now, you're totally welcome to use the way they're doing it, or you can kind of use the cheat way that I've always used, which I think is a little bit better, okay? But you can do it how you want, whatever suits you. Right, in order to calculate lattice energy, basically, you can't actually calculate it experimentally. That's the thing, you can't get values for it. So you have to estimate the values using the principles of Hess's law, which is just like what we did with enthalpy changes in chapter 6. The enthalpy changes that are calculable are things like enthalpy change of atomization, ionization energies, electron affinities, and it's these things that we can use to actually calculate our value for lattice energy. So essentially we use a combination of data about enthalpy change of atomization, ionization energies, and electron affinities in order to calculate lattice energy. And if you remember what Hess's law is, it's basically saying that the end result of any reaction is not determined by the pathway. In other words, you could use a different pathway and have the energy values for that in order to calculate the overall energy change, i.e. the net energy change is going to be the same whatever pathway you take. Okay, right, you're going to have to pause your video and make sure you copy down all of these definitions. And I'm afraid to say you're going to have to learn all of these definitions. So pause the video and copy them. Okay, and in order to understand all those definitions, for them to make sense to us, it's better we just look at examples. Okay, so let's take something like lithium. And we know that lithium, when it forms an ion, being in group 1, it's going to lose 1 electron. Okay, and it's going to form Li+. And then if we look at the definition here, first ionization energy, this is something that was way back in chapter 1 or 2 or something. When 1 mole of electrons are removed to form 1 mole of gaseous ions, that's what ionization energy is. So what I've just written down there is the first ionization energy for lithium, okay? Now, the thing that is missing is, again, state symbols. You have to be talking about the formation of 1 mole of ions in their gaseous state. So I should have state symbols in there. Now, if we were talking about a group 2 element, something like magnesium, again, it's going to lose 2 electrons when it forms its ionic compound. And I'm not even saying what it's forming an ionic compound with, let's say it was magnesium oxide, but it's going to lose 2 electrons. Now, in that instance, effectively, you've got to sum the first and second ionization energy for magnesium, okay? Because it's losing 2 electrons, the outermost electron and the next one, let's say. Okay, so in calculations, if you were dealing with magnesium, you're actually going to find that you're kind of contemplating not only this, but you're also contemplating the energy value for the magnesium 1+ ion losing a further electron, okay, to form magnesium 2+. So you're going to have basically two values there, whatever the energy value is for the first ionization energy and the energy value for the second ionization energy. You're going to have to sum those two values together when you're doing your calculations. So that's an important thing to note. Again, I've missed out my state symbols, so it'd be very important to have that in there. Okay, and the other thing to note is that I'm not quite sure why, because I don't like the way they do it, but you'll see in the A-level textbook that it writes this the other way. It won't write, for ionization energies, it won't write magnesium minus 1 electron to make Mg plus. It will write magnesium makes Mg plus 1 electron. So they actually have this on the other side of the equation, okay? It's the same thing, it means the same thing. I don't like doing it like that, but if you want to do it like that, that's absolutely fine. So I think on this page now, we've probably covered ionization energy definition. So let's just go back. First, ionization energy, when 1 mole of electrons are removed to form 1 mole of gaseous ions. Yes, I think we've covered that, and we've covered what the second ionization energy would be. Now, the number of ionization energy values you're going to be using is depending on what element you're dealing with. Okay, if you've got something that's losing 3 electrons, then you're going to have to sum 3 ionization energy values when you're doing these calculations. Okay, I think it's unlikely they're going to give you ones where you've got multiple ionization energies to add, but who knows. Okay, so let's put a smiley face there. I think this guy is dealt with, and it's one that we've also looked at before, so you should be comfortable with it. Enthalpy change of atomization. Okay, so that's when 1 mole of gaseous atoms are formed from its element under standard conditions. Let's repeat, when 1 mole of gaseous atoms are formed from its element under standard conditions. So let's do a couple of mini equations to exemplify that. Okay, so enthalpy change of atomization. This is actually very, very simple to write as an equation because there's nothing going on with the electrons. Let's take something like sodium. Okay, sodium exists as a solid in its standard state. So there's your solid there. What we're talking about when we atomize that, because there's not much going on really, except that you need to realize that it's talking about the formation of 1 mole of gaseous atoms. So you're going from sodium solid to sodium as a gas, okay? And obviously that requires energy. So there will be an energy value for that, and it's written as delta H. I think it's theta, and then A for atomization. In fact, looking at the textbook, is actually say AT, okay? Some textbooks it's just A. Now, the only slight trickiness would be if you have something that's diatomic. So let's take something like oxygen, okay? Oxygen in its standard state is a gas. So you might think there's less to do here when you express it in the equation, but in fact, because you're talking about the formation of 1 mole of a gaseous atom, so you need to be careful with how you write this. Okay, so we're forming 1 mole of gaseous atoms, okay, not molecules. So there's not going to be a 2 here. We need to make sure that is G, but now our equation isn't quite balanced. Now you might be tempted to put a 2 in here to balance things out, but then you'd be messing up your definition because remember you've got to form 1 mole. So you can't do that. So let's get rid of that. Oops. And hopefully you've probably worked out that you're going to have to put half in here. Okay, so you're going to have to have half of that in there. Let's do another very quick example. Has something like chlorine. Chlorine exists as this in its standard state, again as a gas. And you're going to form 1 mole of chlorine atoms. So again, you're going to have to half that going in. As a side note, because it's very useful to know, if you're talking about changes in energy here, there's going to have to be an input of energy here. So if you think about stability, these gaseous atoms are going to be far less stable than the elements in their standard state. Okay, standard states obviously are tending towards being more stable. That's why it exists like that. Okay, so if I move my face, if I just took this example, we would have the chlorine in its standard state at a lower, more stable energy level than the chlorine in its gaseous state. So if I just draw that line there, oh gosh, terrible line. But again, you can see there's been an energy input here. Okay, so this difference here in energy is effectively what we'd call positive endothermic. So these values are always going to be positive values. This process of atomizing something into its gaseous state is always going to be positive values. So that's also worth knowing. So I think that's probably covered this definition, and we've got examples there to help us understand it. So if we go back to this slide, put a smiley face there. I think we're okay with that. And then we've got electron affinity. Now, I probably should have spoken about ionization energy and electron affinity together, because essentially you can think of these as opposites. One's talking about taking away electrons, and one is talking about giving electrons, okay? So you'll soon realize that you're talking about ionization energies when you're talking about the metal involved in the ionic bond, and then you're talking about electron affinities when you're talking about the non-metal involved in the ionic bond, okay? So let's do exactly what we've done for the other two with electron affinity and just kind of explain what's going on there. So when 1 mole of electrons are added to 1 mole of gaseous atoms to form 1 mole of gaseous ions. Okay, when 1 mole of electrons are added to 1 mole of gaseous atoms to form 1 mole of gaseous ions. Bit of a mouthful, but when you write it down as an equation, it's not too difficult. Okay, so let's just take a random element, fluorine. So you're adding 1 mole of electrons to fluorine, and now this would obviously happen when an ionic bond forms. That's what happens. They get electrons transferred to them. The non-metals pick up electrons off metals like sodium, lithium, whatever. Okay, so it's essentially this, isn't it? It's gaining 1 mole of electrons to form 1 mole of ions. Again, I need to put the state symbols in. Got to get in the habit of doing that. Now this value is generally going to be negative for the first electron affinity value, okay? Because if you think about fluorine, it wants to gain an electron, okay, in order to reach that noble gas configuration, okay? So you can think of it as in going from a less stable to a more stable state, okay? And if you're going from a less stable to a more stable state, then you've got this type of profile, haven't you, with the difference in those values, meaning that it's going to be negative or exothermic, okay? But it's not always going to be the case, because it's common for the second electron affinity to be positive in value. So don't worry too much about it. And just a comment on the word affinity. Affinity is the wanting of something, okay? And if you look at the way I've written the equation there, you're basically saying the energy of wanting a mole of electrons to be added. Okay, so that's for the first electron affinity. And in the case of fluorine forming an ionic bond, you're only going to be using the first value, because it's only going to want to gain 1 mole of electrons, okay? But obviously, if you've got something like oxygen where it gains 2 electrons, you're going to have to be using both values, okay? So similar like when we're talking about ionization energies, where you'd have to combine the first and second ionization energy in your calculations. For electron affinity, you're going to have to do the same thing. For something like oxygen, you're going to have to combine the first and second electron affinity values in order to do your calculation, okay? So looking at your textbook right here, they are using oxygen as the example, right? So I'll just quickly copy that down. So oxygen gaining a mole of electrons to form O1 minus. Okay, need to have gas in there, don't I? Okay, that would be your first electron affinity value, and it's stated here as negative 141 kilojoules per mole. Like I said, it's often that the first value will be exothermic. But of course, in an ionic compound, oxygen is actually going to gain 2 electrons. So you need to add that value to the second electron affinity value, and be very careful here how you're writing it, because your oxygen is already 1 minus charged, and then it gains another mole of electrons to form O with the 2 minus charge. And again, don't forget to put those state symbols in. State symbol, state symbol. Sorry about the messy writing. Now, this second electron affinity value is actually an endothermic process. In other words, it's going the opposite to what my graph is showing here, where you're going from more stable to less stable states, basically. And the value there is plus 798. So it's actually very challenging for that second electron to be added. Don't forget your units, Mr. Starr, kilojoules per mole. Okay, now if we go back to all those definitions, I think we've covered all of them. It's really, really important that you understand them, both in terms of being able to actually kind of repeat them and write them down. There may be questions that ask you to actually define these things, but also to actually understand them in the same way that we've been doing those equations, okay? So enthalpy change of atomization, ionization energy, electron affinity, they are basically the data that you are going to use in order to calculate values for lattice energy. Okay, what is lattice energy? Well, if we go back to our earlier definition, it's the enthalpy change when 1 mole of an ionic compound is formed from its scattered gaseous ions.